for you guys.
Don't brag too much.
Oh, wait.
I know, even me like some days to get out. Yeah.
Let's get started.
I do it twice a week. Overlap.
So what I want to talk about today is
I mean, it's
homework 4.4. I'm going to talk about evaluating intervals. And we're also going to talk about fundamental theorem of calculus. So, last time, we saw the following. We defined what we call the definite integral from a to b of a function f of x dx. This was actually the limit of something that we called a Riemann sum. Which is a sum that was meant to find the area under a curve by first constructing rectangles and then letting the number of rectangles go to infinity and adding up the areas of these rectangles, which we did using sigma. And we got what we called the definite integral. So this is here is called a definite integral. So that's what we saw last time. And right now I want to talk about how we would evaluate such an object. But first maybe I should tell you about some things we want to call, the names of certain things. So this here is of course called an integral sign. The A and B are called the limits of the integral. Where A is called the lower limit and B is called the upper limit respectively. In this case, we can call the function f of x the integrand. It's the thing that we want to integrate, and your dx will be the differential. So it's just how we go about naming these things. So this is called a definite integral. It is definite because it has these numbers on it. And this is called the integral sign. These numbers are called the limits of the integral. That's the integrand, that's the differential. And this is just notation for doing that. And that is just us finding the area under a curve using an infinite number of rectangles. Okay. Now, how would we actually compute such a thing in practice? Well, let's start out with an example. Suppose that is our goal. So, in other words, what we're being asked to compute here can be seen as that. Okay? So someone asking this question is exactly the same as someone saying, compute this thing. Okay. So how would we go about computing that thing? Well, so far, since we're none the wiser, we're adding up. We know that computing that means computing this. So let's actually do that. So here, recall, also from last time, that our xi is going to be a plus I delta x. We saw that last time when we were figuring out how to actually make this thing precise. which in this case is just going to be 0 plus I delta x. In fact, our delta x is going to be b minus a over n, which in this case is just going to be 1 over n. So in other words, I can even think of this guy as I over n. I should have done this first. So now I know what my delta x looks like, and I know what my f of x looks like. Well, I know what the xi in the f of x looks like. Obviously, when I say f of xi, I will be squaring that guy because my function is squaring. So let's actually plug this in, see what it looks like. So obviously here, let's just put it here. This means that f of xi would look like I over n squared, since my f of x is x squared. So this is I squared over n squared. And so this would mean that I can compute this quantity by taking the limit as n approaches infinity of the summation that goes from 1 to n of f of xi, which is this, times my delta x. So how do we go about computing those? Well, remember here, our sigma is using I as the variable, which means my n is a constant. We know there's a property of sigmas that you can factor constants out. So this is really me taking the limit of and factoring out 1 over n squared, and leaving this. And so now, what you can see here is this guy, we have a formula for that. That should be imputed. Because then the formula wouldn't have worked out. But what is the sum of I squared? I goes from 1 to n.
For I squared.
For I squared?
N times n plus 1 times 2n plus 1 over 6.
Over 6. Now, of course, this here is just, this is 1 over n cubed times, this is going to be 2n cubed plus a bunch of things I don't care about because we're going to infinity. And the highest powers are going to be controlling everything. So really what you see here is this is 1 over n cubed. I can just multiply it, and this is 6 over n cubed. And so you get 1/3 of these. Turns out the area under the graph of x squared on the interval 0 to 1 is 1/3. Now, let's by the way, I think we actually did this example before. There was a point, maybe last class or the class before that, where we actually computed this specific example. Right? This was, it's actually, I was actually asking you what was the area under x squared. That means if you were to graph y equals x squared, and you look between 0 and 1, the area here is going to be 1/3 units, whatever the units that you're measuring on the axes. Now, here's something we're only going to consider. I'm not going to completely do it, but consider if someone were to ask you this. Well, what if I wanted to find the area from 1 up to 5 of x cubed plus x squared plus 1. Let's say someone wants that, right? So there's this graph. You want to find the area under that graph on the interval 1 to 5. Now, how would that actually look if we were to do this? Well, we'll go through. We'll first find our delta x, which is b minus a over n. It's 4 over n. We will then find our xi, which is going to be a plus I times delta x. That is going to be 1 plus 4I over n. Then we are going to find our f of x. And that's going to look like, well, that's going to look like 1 plus 4I over n cubed plus 1 plus 4I over n squared plus 1. And so this would mean that to compute this guy, I would have to actually compute the limit as n approaches infinity of the sum, I go from 1 to n, of f of xi times delta x. And immediately you can start to see, yeah, we can do it, but it's starting to get a lot more annoying the more complicated we make our functions. I'm going to have to cube a binomial, then square a binomial, then multiply everyone out, factor the constants out of the sigma sign, apply these formulas I know. And by the way, I only told you formulas up to I cubed. If of course I had a 4th power here, then you're going to have to figure out what is the formula for that, right? If you have a half power here, what does it mean to add a bunch of square roots? What's the formula for that? Clearly you can see this gets annoying. Gets annoying pretty quickly. Now, you do have to know how to do this. I am going to ask you to actually do this with a problem, but it's not something that you're going to want to do all the time. Much like with derivatives, we had a definition for it that says, you know, to find the derivative of a function, you find this limit. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. But clearly, that kind of got cumbersome a lot of the times. And so similarly with this one here, yes, we know by definition how to compute this, but it kind of gets cumbersome some of the times. So now we're trying to say, now we'd like to know, is there a nicer way? And the answer is yes. And so, how would we go about finding this nicer way to do these computations? Because yeah, we went from a situation where you had to have some guy that you hired to count all these rectangles and add up their areas, to this nice formula where someone can just compute it. But again, even the computation itself can get really annoying really quickly. Now, if we're dealing with an unfamiliar function that we really don't know a lot about, this is probably the only game in town. You have to kind of suffer through it, brute force. But there are going to be a lot of functions by which we don't have to do this. And so now we want to actually find a nicer way. Now, you might also recall we saw a connection between velocity, or let me state it in a different way. We saw a difference between the change in distance and the area under the velocity curve. You might recall we actually derived in our made-up example that if I were to find the area under v on AB, then it turns out that that was just the position function, the distance function, evaluated at B minus the distance function evaluated at A. And then we started to wonder, could something that nice work in general? And so when we were realizing that this is what we have to do all the time and we're trying to find a nicer way to go about things, there's this example that seems to suggest a nicer way of going about things. And here's what we really care about, finding an area. But it turns out that we can think about an area as a subtraction of a certain function. What function? In particular, the antiderivative of the function. But we saw it here in this specific example. It's not good enough for us to extrapolate that in general. We have to kind of prove that that would work in general. And so, using that as an excuse to try this daring proof, we developed something that's called the evaluation theorem. So this inspired it's called the evaluation theorem. Some people, out of respect for our forefathers, call this the Newton-Leibniz formula. A lot of people, most people will in fact know it as one of the parts of the fundamental theorem of calculus. It basically says if f is continuous on, you actually don't need continuity here. You need continuity for the other part, but let's just pretend everything is nice. And f is any antiderivative of f, then it turns out you can find the area under f on the interval AB by actually finding the antiderivative and evaluating it at B, and then subtracting the evaluation of the antiderivative at A. So it can actually compute the area by evaluating a function, a particular function, or one of a class of particular functions at a certain point. This is called the evaluation theorem, because we can now compute areas just by evaluating some function. Now, why should that be true? Well, let's actually look at it. Okay, so it's going to be easier for us to start with something like this. So we want to start there, and we want to get here. And we remember what this means. This actually means there's going to be a limit as n approaches infinity of the sum of f of xi times delta x. I goes from 1 to n. So we realize, okay, so this guy is a sum of a bunch of things, right? We're adding up n things and then we're letting n go to infinity. Here we only have two things. So the first thing you might want to realize is that to change one side of a formula into another, you want to try to make it look as much as the other side as much as possible. And hopefully this is possible, and we'll end up getting a nice answer out of it. So the first thing is to do is to start renumbering things the way that we did before. So remember, our b is always going to be our f of xn, and our a was our f of x0. So now we have to realize, where will we get all the other xi? Well, you can do that thing that math people like to do. Let's throw them in. We're going to add and subtract things in a very convenient way. So that's what we're going to do. So I'm going to subtract f of x minus 1 and add f of x minus 1. Then I'm going to subtract f of x minus 2, n minus 2, and then add f of x of n minus 2 plus Okay, so I'm doing a lot of this stuff. Okay, plus, ultimately, let's do the last few. I would end up with x2 minus f of x1 plus f of x1 minus f of x0. Okay? So I'm adding and subtracting all these middle terms, right, to get in the other xi's into the play. Now, here's where something magical happens. An unlikely hero comes into the fray. And here we have a difference of a function. Okay? And here we have two x coordinates, kind of separated by that function. And this kind of reminds us of a derivative, right? It's like that f of x plus h minus the f of x, right? There's an x value and then there's a one a little bit to the right of it, and there's a difference here. And so we can actually say this is going to be so. Now my question is to you, why can I say that? What did I actually apply here? Where the Ci are just some element that lives in the set I and -1. What allows me to actually say that? Well, this happens by the mean value theorem. Right, recall what the mean value theorem says. It says f is continuous, then continuous on AB, then there exists a c in the interval AB such that if we take the derivative at that point is equal to the average rate of change. In other words, I can take a difference of a function and I can replace it by its derivative evaluated at a certain point in between a and b of b minus a. So I can take this kind of expression and replace it with that kind of expression. That follows by the mean value theorem. This follows by the mean value theorem because, and I can apply this to the big F, which is what I actually did here. I applied the mean value theorem to big F because I know big F is continuous. How do we know that big F is continuous? Think about it. I'll ask at the end of class. We'll see. Maybe I'll throw in some free quiz points. How would you know that big F is continuous here? I'm telling you it's continuous, but how do you know? Anyway, we could do this. Add and subtract a bunch of things, so I'm not changing the value of anything. I can replace each pair of subtractions by this. It follows by the mean value theorem, because big F is actually a continuous function. You should really know why it's a continuous function. However, I have that. Now notice what this guy is. In our conception of the world, this length is just always going to be the same all the time. That's the length that I call delta x. So in other words, what I get is know, by definition, big F is the antiderivative of little f. Therefore, f prime gives me little f. And what is that? Well, we now have a nice way to write something like this down. I can write this as a summation. This is f of ci times delta x, where my i's go all the way from, let's say, 0 up to n. Now what I can do is take a limit as n approaches infinity of both sides of this equation. And then what's going to happen? Well, the left side doesn't have any n's in it, so it just stays the same. So I'm just left with f of b minus f of a. The right side, however, is literally what the definite integral is by definition. I mean, sure, the numbers are slightly off, but we're going off to infinity. Starting in one place versus another is not going to make a difference. That is actually this guy. And this is called the evaluation theorem. This gives us a nice way of actually computing integrals without actually having to go through the summation sign. Now, of course, it assumes that you would have knowledge of what the big F is. If you don't have knowledge of what the big F is, then you kind of have to brute force this way. But if you do have knowledge of what the big F is, then you can actually use the big F to find an area. And that is going to be a lot simpler because we actually do know what the big F would be for a lot of F's. At least in calculus, right? So we would be able to figure out the big F for if F is a polynomial or a trig function or a square root or any of our familiar functions, an exponential, a logarithm. We can figure out big F. So this will actually help us out in a lot of the situations that we care about. Here's another thing. Also, here's something interesting. Suppose we define a function in the following way. I define a function in terms of an integral where a is a constant. Now, at first you might think that's weird. This happens all the time. There's a lot of situations in which we figure out what a function is by anti-differentiating something else. So let's say we know that there is some function that we can describe on some interval a to x as the antiderivative of some other function. And let g of x be an antiderivative of the f, right? So that means if I take the derivative of g, I get the f. Now here's the question. What is f prime actually equal to? Or in other words, I can say what do you get if I would differentiate this expression? What happens when you differentiate an integral? This is the question I'm asking. Well, here's what would happen. So if my f of x, big F, is equal to this thing, and I'm not necessarily meaning big F as the antiderivative of f, even though I'm being quite suggested by that, but big F is just representing some function defined this way. Okay? So it has limits, lower limit is a, upper limit is x, a is some constant. Then by the evaluation theory, this means that big F is actually equal to big G evaluated at x minus big G evaluated at a. Right? I can compute a definite integral by finding its antiderivative and plugging in the limits. Plug in the upper limit, subtract the lower limit. Okay? That's what the evaluation theorem says. Now what I can do is I can find the derivative of both sides. Now the derivative of g of x is just going to be g prime, and the derivative of g of a is just going to be 0 because it's a constant. In other words, taking big F prime gives me g prime. But what is g prime? Well, g prime is f because it's an antiderivative. That is, if I have a function that's defined as an integral, and I differentiate that function, the result will just be the original function that I was trying to find the integral of in the first place. In other words, a nice concise way to write down this thought. If I take the derivative of an integral, the result is just going to be the original guy. In other words, a derivative reverses an integral. So earlier when I said, integration and differentiation, they're kind of two sides of the same coin. They're almost inverse functions of each other, inverse operations, I should say. This is where the almost comes from. You see, a derivative will reverse an integral, but the integral doesn't fully reverse a derivative. If you try to reverse a derivative, you get what's called an indefinite integral, right? So there's going to be some missing information. So it's not a perfect inverse. It has a lot of the properties of an inverse, but not everything. We can't recover all the information. However, a derivative will reverse an integral. So if I take the derivative of an integral, it's like it didn't exist. I get the original function. Now these two facts together, so the evaluation theorem and what I just showed you, form that thing I've been teasing since the day one, the fundamental theorem of calculus. Now I know we proved this all, you might not realize how much of a big deal this is. I mean, we proved it in what, like 20 minutes? But really, it took centuries of development to get to this point. I mean, we've really fast-forwarded the clock here by a lot, right? So if certain things I've tried to explain are a little bit choppy, you have to understand I'm really trying to summarize 2,000 years of mathematics here in like a 3-month time span. Some things are going to be kind of a little bit choppy. But this is called the fundamental theorem of calculus. This is why we're here. This is why calculus, modern day calculus as it is studied the way it is, because of this theorem. If f of x is continuous. And you need continuity for this, but you don't need continuity for the first part, but I just like to, most people just like to assume continuity, so. So assuming you have a continuous function and you have an antiderivative of that function. So you know something that if you differentiate it, you get that function. Then two facts hold. One, this is called part one. You will be able to find the area under F by evaluating its antiderivative at the endpoints of the interval. And two, this is often referred to as part two, or the second fundamental theorem of calculus. If you take the derivative of the integral of F, the result is F. This statement is the fundamental theorem of calculus. It is the connection between finding the rate of change of something and finding the area of something. Two things that were thought of for a long time, centuries upon centuries, as being very distinct, different things, we now realize are somehow intimately connected. And we know that by this theorem. And this allows us to actually push each theory beyond its limits, pardon the pun. Okay? So just knowing that everything we studied here is kind of like studying this thing in reverse, and everything we studied here is kind of like studying that thing in reverse, then we're able to come up with ideas in this sphere that we got from that sphere, and so on and so forth. And so knowledge starts commingling because we now have these two bodies of knowledge coming, and now each of them informing the other, and it took off. And now we have calculus and a lot of other things that came from calculus. Calculus is really probably the foundation or the birthplace of modern mathematics. I mean, there are mathematics that are not calculus, but really the way we started thinking about math, calculus is really the thing that started that thing, this kind of commingling of ideas to create something that's much bigger, much larger, much more sophisticated. And this idea that, oh, there are a lot of times we think we're studying things that are totally different, and it turns out that they're actually kind of the same. They're all the same thing. It's one big part of a story, and you have people who know different chapters of the same story. Let's figure out what the entire book is. That is math research. Let's figure out how all these things are connected. Let's figure out how to push these things. And in fact, something I mentioned last time, not last time, a few classes ago, about Vermonts' last theorem and about how it took like 300 years for someone to prove it. It turns out that they went into a direction. They got something that seemed to not be connected at all. That was the secret to proving the theorem. Right? So he was looking at equations that look like this. Right? How would you solve that equation like that if you're forced to live in the integers? Right? Are there an infinite number of solutions, or are there only a finite number of solutions? And he turns out he went to an area of math called elliptic curves, which it's a pretty heady kind of math, right? This is the kind of math where you're drawing graphs where you make infinity just a point on the graph, kind of like a hyperbolic universe. And yeah, that's what he used to figure out the answer to this question, which was normally thought of as a number theory question. So everyone was trying to solve this problem for centuries using all their ideas from number theory. He went and got ideas from somewhere completely unrelated and then tied it back to that. And that was the breakthrough. And that's the kind of thing that we have learned from calculus. It's really a fundamental theorem, not just for calculus, but for how we think about math in general. It's a really spectacular theorem. And not that complicated. I proved it in less than 20 minutes. But really, to get to the point where we had all the ideas in place to be able to prove it, it was a long journey. And it's also worth mentioning, sometimes people label these in the opposite order. So I prove this, and then I use that to prove this. It's also possible to use this to prove that. So some people might start here at part one and call that part two, and vice versa. When I was a little Javon growing up, I knew that as part one, and that's how I always thought of it. And after I became an adult, I realized, there are a bunch of, there are times when I'm taught, oh, the second fundamental theorem of calculus, and I hear someone quote this, and I'm like, no, the second one. And they're like, I did quote the second one. What are you talking about? This is, and then we get into an argument why you want, it's really, it doesn't matter. So, but I call this part one and that part two. It's completely fine, and you'll hear people do it the other way. Don't be confused by it. Neither of us are lying to you. You can actually prove it in either direction. And so, whoever sees this first, we'll call this part one. Who sees that first, we'll call that part two. But you can use one part to prove the other in either direction. So, at this point, what I really should do is tell you about some more theoretical stuff, but I think we are too, that's going to be too much, for the kids watching at home. I know you guys enjoy this, but for their sakes, let's just do some examples. So I'm going to write down a list of examples. We are not going to get through all of them. We'll finish it next time, but I just want to start. Two sets of examples. I'm going to have you do one for a set of examples to get you familiar with part one, and then another set to get you familiar with part two. And once we figured out this connection, we went back and we used the notation for antiderivatives with the integral sign, and that's where that came from. So we already did this. That's what I had listed as my first example. Second example. Oh, no, maybe we should do it using the shortcut. We did this using the summation series way. Let's do it another way. And let's do that. And let's find the area under a cosine graph. And let's find that area, which is going to spark some interesting discussion. Spoiler alert, the answer is 0. You're going to be like, how would that make sense? Okay, we'll talk about it. Let's look at this guy. Cosine squared of x. That's 0 to 13. That's sine squared x plus cosine squared x. That's going to, man, I'll spend the rest of the time writing these examples down. Okay, 1 to 4. To be fair, this is something that you're going to be expected to be able to compute relatively quickly. So I really want to do the kind of drills kind of examples. That's where we just brute force a lot of them. So we'll start us slowly with those. And as well as so that's some examples to get you used to computing things you would need to know for part one. Here are some things for part two. This is example 1. There's that many parts. Example 2. Find the derivative of the following. one thing you should appreciate is that there are some of these guys where you actually can't first find the antiderivative and then differentiate that result. You have to actually go through part 2. Turns out something like this kind of function, it doesn't have an antiderivative. So that'll be, so you really have to use the fundamental theorem here. So there are times when we couldn't figure that out, but now with the fundamental theorem of calculus, it's no problem. Yeah.
Is your question you posed earlier, is it because big F is continuous because you know it's differentiable because, well, big F is the antiderivative of small f, and you told us that small f is continuous, and
yeah, small
that
f's
makes
continuity has nothing to do with it. It's what
Well,
you
then-
said before.
so big F is differentiable, and if
Big
it's
F is
differentiable everywhere, then it must be
Differentiable means
continuous.
continuous.
Yeah.
Right. We had a theorem early, way back when that said something is differentiable, it's automatically continuous. The other way is not true, but differentiability implies continuity. So yeah, we know it's continuous because it's an antiderivative. By definition, it has to have a derivative. If it has a derivative, by definition, it has to be continuous. It has to exist for us to draw a tangent line to it. Did you Google that?
That's what I thought it was, and then I texted my older brother, who's a math major, and double checked.
I want to say this. Does it check out?
Yeah.
We'll stop there. I mean, we won't have time to actually get through any of that.
Cheers.
Yeah, next time we'll kill all these examples, and then maybe we'll go back to talking about some more abstract properties and some other thing that can help us compute things.